And the second part, also a very important part, is the isomerism. So I put a French picture, a picture in French here, which is good because I want you to take some notes, not just look at the English. Oh, you definitely can say methanoid instead of formate, and it's a more formal name. Okay. So isomers, we know they have the same formula but different structure. So we can divide it into two big groups. The first one is called structural. You also see something constitutional. So both of these two have the same meaning, which means they have different connection. Connection is different. They have different connection. So the second big category is called stereoisomer. What does it mean? Which means they have the same connection, but they have the different arrangement or orientations in the three-dimensional world, right? For example, if you compare these two, obviously the fluorine is connected to a different carbon. So this is called structural or constitutional. So structural constitutional are easy. We want to put more time on the stereoisomers. So we keep going. So one type is called conformational. What does it mean? Which means it's related to the rotation of a single bond, right? So you will see what are those two molecules? Actually, they are the same molecule. What is the molecule? They are both butane, right? And the normal butane. So we kind of use a Newman projection. We project through these two carbons. You kind of, you observe from this carbon bond, right? Okay. We also have some nomenclature here. What is the first one called when these two methyl groups are close to each other but not overlapped? Actually, I'm always confused how to pronounce this word. It's called gauche. Am I correct? I don't know. What's the meaning of the gauche? A gauche? I don't know. Anyway, it's G-A-U-C-H-E. What's the meaning of this word? Oh, it's just called 60-degree angle, 60-degree off. Okay, and then the second one, the two groups are in the opposite side. What is this called? It can be called anti. Is there any other name? Stagger? I'm not very sure about stagger, although in the USNCO Local 2019, this word was appeared, right? Stagger means, I don't know. You guys can do some homework. I'm always confused by this kind of weird words. How about this one called? This is kind of fully overlapped. It's called eclipse. I think eclipse makes sense, right? It kind of, the eclipse. The sun is blocked by the moon, right? This is kind of the sun and the moon. So is this also called stagger? Probably, I think so. Yeah, it can be called anti. No? So what is the stagger? Ah, I kind of agree with Jay's idea. Stagger include both gauche and anti. I will do some homework. Okay? But I think I kind of agree with, Jay's idea. Okay? So which means both of these two are staggered. And now it makes sense because the question in the USNCO Local 2019 is ask you why the cyclohexane is stable. So the first option, the first statement mentioned about the bond angle are close to 109.5. Obviously, this is correct. The second option is all of the hydrogens are staggered. I think if our staggered definition includes both of these two situations, is correct because these two hydrogens, they are anti, but these two hydrogens, they are gauche. So if we combine these two together, if they are called staggered, I think it makes sense. The local exam is supposed to be posted in the website tomorrow, April the 8th, although sometimes, they delayed or due to some reasons, I don't know. Okay, let's keep going. I will double check the stagger, but I pretty much kind of agree with the idea we shared here. I need to do some erasing. Now it's a little bit messy. Keep going. So conformational actually not so important in isomerism because it's not a real isomers. They are not isomers because you cannot separate the two conformations because they are changing all the time because they are slightly different in energy, right? And then let's have a look. The next one is called configurational, although this word is not so common used. So it doesn't matter so much. And then there are two categories. One is called Enantiomer. Enantiomer means the molecule is chiral, and the two molecules, they are mirror images. This is called enantiomer. Another one is called diastereomer. Diastereomer means they are stereoisomers, but they are not enantiomers. One more time. Diastereomer means they are stereoisomers, but they are not enantiomers. So you will see there are one very typical category goes to the diastereomer, which is the cis and trans for the double bond. So obviously, they have the same connection, but they have the different arrangement in the three-dimensional world. So they are not structural isomers. They are definitely stereoisomers. But those two, they are not mirror image relationship. So they are not enantiomer. So we need to classify these two into either cis and trans. If cis and trans option is not available, they should go to diastereomer. Okay. Another thing is called aptamer. It's something like this. So we have multiple chiral centers. A lot of them are the same, but there are something different. For example, here, 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 here. All of those 5 carbons are chiral, right? But the first 4, they are the same, but the last one is different. Aptamer, I don't think you need to know the words. I believe it should be like this. And the last one is called animal. I don't want to give you too many words like this. It really doesn't matter. The keyword we need to know is diastereomer, okay? Because this kind of stereoisomers are very complicated. So I have a few questions listed here. Obviously, we will answer the first question. My second question, alkenes, why alkenes have cis and trans? Can you give me a keyword? Why alkenes? Yes, the double bond, right? The double bond cannot be freely rotated, right? It can be rotated, but it cannot be freely rotated. When can it be rotated? When we put energy in, right? So actually, this is related to our vision. We need to put energy in, break down the bonds, and rotate the bonds, and change the cis into trans, right? How about alkanes and alkynes? Obviously, alkanes, single bond, freely rotated. Alkynes is a linear relationship, so although actually it cannot be freely rotated, but even if you rotate it, it doesn't make any change, right? It's linear, so both of these two does not have the cis and trans. Next one, can you read the question and think about it and let me know what's your answer, yes or no? This is the compound, right? So we don't have the cis and the trans, okay? No problem. How about this one? Uh-oh. What is the relationship of these two molecules? They are the same. You just flip it. They are identical, right? Optically active. I don't want to talk too much about this. You guys can read a little bit more by yourself. Basically, it will shift or rotate the polarization plane of the single polarized light. So this is something very complicated in physics, but in chemistry, in organic chemistry, we just need to know what is the general idea of optically active. If it can rotate the single polarized light into a different direction, it is called optically active. Otherwise, it's optically inactive. How it is related to chiral? If a molecule is chiral, it will rotate the single polarized light, and then we call it optically active. And then how to judge a carbon is chiral or achiral? Basically, you need to have an sp3 hybridized carbon connected to 4 different groups, right? So let's say if you have, how about this one? Is this one chiral? Is achiral. So we can try to draw a mirror image. Are those two molecules superimposable? They are, right? So if you rotate through this bond by what is the degree? Let's say 109.5 degree, you will see. No, it's not rotate here. Let me see how to rotate this molecule. Yeah, we need to kind of flip this molecule in this direction, put the hydrogen of here into here, and then you will realize these two are the same, right? You guys can do the rotation or flipping by yourself. So anyway, you need to have 4 different groups connected to the same current. I think we already answered question E. Oh, the last one, very important for USNCO National. One is called racemic mixture. Another one is called meso compound. They are both optically inactive. What is their difference? Racemic mixture is a mixture. It's not a pure substance, right? It's a kind of 50% of 2 enantiomers, for example. I think most of you got it. So if you have 50% of the left one and 50% of the right one, so the left one may rotate the single polarized light into one direction with a certain degree, and the right one will rotate into a different direction with the same degree. So they are kind of canceled with each other. So this is why they are optically inactive. This is called a racemic mixture. And meso is a pure substance. Meso is you have multiple chiral centers, but the overall molecule is achiral. Let me give you an example. Let's still use the cyclohexane. Is this a good example? This is not. Let me use another example. I may have to use Fisher projection. So there are 3 chiral centers here, here, and here. Obviously, you can try to conclude a R or S to the 3 chiral centers, but now you realize there is a mirror plane here which will make this molecule symmetric to each other in the molecule, right? So this kind of stuff, multiple chiral centers, but there is either a mirror plane in the molecule or a involution center in the molecule is called meso. It's called meso. And then it's a kind of the top half polarize the light into one direction, and the bottom half kind of change the direction of the polarized light into another direction. So they cancel out internally in the same molecule, right?